Hello guys, welcome back. And in this session, I'm just gonna talk about platform level interrupt controller in RISC-V. So the PLIC or platform level interrupt controller is a separate specification now. It was initially part of the RISC-V privilege spec and later it was moved out. So the primary objective of PLIC is to route the interrupts from the platform level interrupt sources to one of the hot context. So as you know that RISC-V is a scalable architecture. So on a single platform, there can be multiple RISC-V cores. So any platform level interrupt has to go through some kind of arbitration to decide and forward or choose a particular hot context. And by hot context, in RISC-V, it means privilege level for a given hot, okay? So that's a hot context because in RISC-V, interrupts can be enabled or disabled and can be delegated to different privilege levels, okay? So this block which sits here is what we are going to focus on this session. And so I'm not just going to go through the spec. I will also see how this PLIC is implemented in FE310 RISC-V Core. And later we will have a sample application on how to configure the PLIC in FE310 Core and toggle the toggle a LED on the Hifive1-Rev B board. Okay. So before I go further, I would also like to remind you that so the core interrupts or the local interrupts that are specific to a particular core are handled by the core local interrupter, and this PLIC comes into picture only for the platform level interrupts. Okay, so that's the overall interrupt flow as per the PLIC specification, and it's a very simple protocol. So the interrupt source can be one of the platform level interrupt like GPIO or SPI, whatever it is. It just signals gateway. So these gateways and PLIC cores can either be a logical entity inside a single physical hardware, or it can be an separate physical hardware by itself as well. Okay, and these flow here, which are highlighted in red, these can either be wired, like these notifications can be wired, by which I mean it can be a bit flip or a signal level difference, this which can cause this notification, or it can be a message by itself. So PLIC specification supports both wired and message signal interrupts. Okay, so this once the source signals the gateway, then the gateway would raise an interrupt request to PLIC core, and so these are not just direct forwards. A lot will happen here, and a lot more things are checked here, and then the PLIC core would notify a target. So at this level, it can be a multicast, because if there are many targets, then this notification would be sent to all targets which have for which those this interrupts and the corresponding priority levels and everything, if that has been set and enabled, then it would be a multicast. Then one of the target alone would be able to claim and get the interrupt. So few things happen atomically, so that this prevents uh, no two targets. This won't allow two targets to claim the same interrupt. So that's not possible due to the atomicity involved in this. I'm not going to go deep into the atomicity, but we will see how it works later. So this section, or the claim and getting the response, and then once the interrupt is handled, notifying back that the interrupt completion to the gateway happens inside the interrupt handler. Okay, so this would be more clear, and will it'll be more easy to understand once we see this implementation in FE310 core. Okay, so in the case of FE310 RISC-V core, so these are all the interrupt sources. If you can check from the manual. So as you see that each peripheral have been given a source. So there is only one interrupt here, so it can be always on watchdog. I've been given the source number 1 and GPIO. So this there are 32 GPIOs, so the from 8 to 39 sources are given to the GPIO, and so this would correspond. So this interrupt sources is what is mentioned here. Okay. So now in Hifive1 revision B board, if you see the GPIO pin 21 is connected to a blue LED, and that's the one we would be blinking later in the exercise. But this how the interrupt would flow for this GPIO 21 is. So for GPIO, the source corresponding to the GPIO is 29. If you go back here, so the GPIO 0 all the way 32, it starts from, so there are 32 instances, so 8 would correspond to GPIO 0, and if you find, if you calculate, then you would find that GPIO 21 would correspond to source 29. Okay, so when this interrupt is raised at the source, that would signal the gateway, and the two primary objectives of gateway is that it would convert global interrupts like the edge triggered, level triggered, or low level or high level triggered. Those kind of interrupts would be converted into one common request. Okay, and that would be forwarded to the PLIC core. So whether it is a high or low or edge, this PLIC core would just get the same source interrupt, that is, which is 29. And in FE310, this is a wired notification. So if you see here, we'll see later that this request would be latched at a bit position on this register. Okay, and then the PLIC core would notify the target. This happens in FE310 by setting the machine external interrupt pending bit in the CSR. Okay, and the MIP CSR, and then the target would claim an interrupt. It would just read from this register, and so this read would, if the read value, if the read value is 0, that means that there is no pending target, no pending interrupt for this target. It is possible that a target can be notified by an interrupt, but by the time when it claims, some other target might have claimed the interrupt. But the claim and the clearing this bit, this happens atomically, so that no two targets would be able to claim the same interrupt. Okay, so once the claim is done, and the PLIC core would mostly return with the highest So the red value would mostly be the highest priority interrupt pending for the target would be returned, and then the interrupt would be serviced in the handler, and then the target would notify that the completion, the interrupt is serviced by writing back into this register. So this bit positions and this read write register where memory addresses are specific to FE310 core. Okay, so if you go back, that's what here I have exclusively mentioned that PLIC is memory mapped, whereas if you see the CSRs in the core, those are all like hardware registers, but the PLIC is memory mapped. That's why you see these registers or register addresses here. So as I've said before, at each stage, a lot would be checked. For example, before this PLIC core notifies a target, it checks if this target priority. So this each target can set its own set of configuration, like what kind of interrupts it is interested in, and what priority level of interrupts it needs to be notified, and if the interrupt uh, for that core has been enabled or disabled. All this are checked before target is notified. At the same time here, as I said, the gateway would ensure that when there is a interrupt already requested to PLIC core for the same source, it wouldn't again forward further interrupts for the same source. Okay, so these are this would prevent from the burst of interrupts being forwarded. So that's how the PLIC is implemented in FE310 Core. So this is the a block diagram from the PLIC specification. Okay, so this part here is the PLIC gateway. So whatever we saw in the previous interrupt flow diagram. So the gateway, so this is that block. So from the gateway, the interrupt request comes to the PLIC core. So this is the interrupt request, and this block is the PLIC core. So going back to the picture, for PLIC to do all this, then PLIC needs a set of registers. So let's see what are all needed for that. First one, PLIC core allows interrupt priorities to be assigned for each source, to each interrupt source. Okay, so the priorities from 0, there are I think 0 to 7. So the other priorities that PLIC allows to configure for each source interrupt. Then for each target context or each hot context, uh, the PLIC can be configured to either to enable or disable the external interrupt. Then it also allows each core or each target to set the maximum priority and interrupt threshold. Uh, so based on this, PLIC would forward the uh, interrupt notification to the target. Okay, not forward. So based on this settings, PLIC would notify the corresponding target. So if you see here, so there should be a, since PLIC core is memory mapped, you need a register for priorities register. So that's what it's listed here. So there should be an register to set the priority for each source, and there should be an register to enable the interrupt. That's what this enables. And then priority threshold here, the threshold beyond which the interrupts can be forwarded or notified to this particular target. And then, as I said, the claim and complete register for the claim and completion notification. So you need a register for that. Okay. So now, based on this, and since PLIC is memory mapped, the PLIC specs, the PLIC spec has this following memory mapped, or this is part of the spec itself. So the base address of the PLIC is implementation specific, and then at each offset, what that register should correspond to and what is the functionality is part of the spec itself. Okay. So from the base till the first 1023, so the interrupt 0 is always reserved. So there cannot be an interrupt with the source 0. So from source 1, and the PLIC has a maximum, PLIC allows the maximum of 1023 sources. So first 1023 registers should be used to set the priority for this interrupt sources. But some hardware, or it's if the hardware doesn't have 1023 interrupt sources, if it just have one or two, then from the base address and the next two addresses would be reserved for that, and rest all, first two would be used for the number of interrupt sources supported in the platform, and then rest all should be reserved. And the base plus this offset should be used for the interrupt pending bits for the source, and the base for plus 0x2 followed by 3 zeros offset is for the enable bits and interrupt enables. And then, so this enable bits, or like, so based on number of contexts, if there are, it supports up to 15871 context. That means that can be, each context can be a separate core and a separate heart, or it can be a one core with 2-3 privilege levels that would correspond to, because in one core, each level would correspond to a context. So based on the hardware support, that many registers would be used for that. And finally, for the priority threshold and the claim complete register, this is how it goes. So base address plus offset. So for context 0, the priority threshold followed by the claim and complete notification register for each context, and then it is reserved, and then followed by the context 1, and it goes up to the context 15871. So the good thing about this is that it clearly says the offset, and so it's very clear. But the drawback of this is that it would be highly inefficient in terms of memory usage, because you see a lot of memory would be, if the target supports only, let's say that it has only two interrupt sources, then only though it would use just base plus 0x4 and 8, but rest all up to FFF0, it has to be, not sure if that can be used for anything else. So it has to be left reserved. And then the next can only start from this offset and so on. So that's one drawback of this. Okay. Now, how this maps in FE310 is, so in FE310, there are 32 interrupt sources. If you go back to this, sorry, not 32, 52. So there are 52 interrupt sources, and 52 correspond to I2C. So 52 sources, and so the first 52 registers are used to set the priority of each source, and then there's a reserved block. And for interrupt pending, yeah, you just need two registers, because a bit can be used for a source, so that would correspond to just two registers, and rest all are reserved here. And in FE310, there are only hard 0 M mode context alone. So just two registers for that. And for the hard 0 M mode, then the next two register, one for the priority and the claim and complete registers, or on the last offset. So if you see here, this offset should match, for example, the source offset would be from the base plus 0, and then base plus 0 x 1000 should be the pending. So base plus 1000 should be the pending here. And this is for the priority and threshold. So since there is only one context in FE310, this is how it is, as you see, as I said before. So you see there's a reserved block here, which would result in a very inefficient way of using the memory. So now that we have seen the PLIC specification and the implementation of the same in FE310 Core, so next I'm just gonna demonstrate and sample application which configures the PLIC and blinks blue LED on the Hifive1-Rev B board. So if you see here, this at this part there is a blue LED on the Hifive1-Rev B board, and the sample code would just blink that blue LED alone. Okay, so the code whatever I'm gonna use in this video is already available in the Github repository. And if you go to this repo LearnRISC-V in the GitHub, so this is the directory structure, and that's right now only one application and support for only one board, which is Hifive1-Rev B board, and all the code are in RISC-V assembly. And there's a build script and the tools right now, the OpenOCD configuration script and the linker script for the Hifive1-Rev B board are in the tools directory. Okay, and this build script right now does not download any of the toolchain. Instead, it would just invoke the compiler and the assembler and the linker, assuming that you have installed those toolchain in your computer, and you should have exported, the path should be exported to this script. Okay, and to command the command to command sorry to build for a particular target, you have to just issue /build.sh followed by the board which you want to build and the application whatever. So right now it is just the one option, that is Hifive1-Rev B board and GPIO 21-on-off. Okay, and going to the application, so this is the main file or the app entry file for this demo application. So this file would invoke functions all from the assembly code available in the corresponding board directory. Okay, but if you go to the application main file, so this would be the app entry point, and okay, so this is the app entry point, and this first block, this complete block, what it does is for all the interrupt sources available in Hifive1-Rev B board, it would set the priority as 2. Okay, and I will explain why it's set as 2 here. And so this loop would loop through 52 source ID, and it would set the priority as 2 in the PLIC core. Okay, then this would just clear if there is any GPIO RISC interrupt already pending on the hardware. Okay, so this main or in this file, the interrupt is configured to be triggered for the rise, signal rise on the GPIO 21 pin. Okay, and once the priority is set as 2 for all sources, just for the GPIO 21 pin 21 alone, the interrupt priority is set as 3. So, and then the PLIC threshold has been set as 2. That means that any interrupts from 0 to 2 would be masked, and any interrupt with the priority above 2, which is so in this code, just GPIO 21 alone would be what is that? Would go through the PLIC, and the core would be notified. Okay, so that I just want to ensure that whenever there is a uh, entry into the trap routine, that means that the trap or the interrupt should be generated only for the GPIO 21 interrupt alone. Otherwise, there will be a lot other RTC and other interrupts, and it would keep interrupting the flow of this application. Okay, and so the priority is set and the threshold is set. Then in the interrupt module, the external interrupt and the PLIC source is enabled. So if you see the function naming convention here, the FN stands for function, and the next string would represent the module. So here it is GPIO, and this is PLIC, and this is just the interrupt, so on. So this configures the GPIO as 21 as input as well as output, because you need to configure as output to send 1 and zeros on the line, and you need to configure as input to sense the signal rise on that pin. Okay, and then enable the interrupt for the um, signal rise on GPIO 21. So that's the configuration of all the basic configuration that is needed. Then that's a control block where it would write just very first it sets 1 on the pin, and there's a delay, and followed by a 0 and then another delay. So I could have merged these two into one single delay and a write, but I just want to keep this flexible so that the on delay and the off delay can be configured separately. Okay, so now let's build and run that. I have already cloned. So this would just clean whatever has been built before. So this is the board name, and this is the app name. So this would generate the executable final underscore load.elf here. And let me so now the GDB session is established. I'm just going to load the code. So based on the linker script, this code will be loaded only in the RAM starting from this address. Okay. Now if we just run, you can see the LEDs blinking here. So let's do some code inspection and see if the code works as per whatever we discussed and as per the PLIC spec. So what I'm gonna do is just gonna quit from GDB. Control C. I'll just reset the board. So instead of executing the code continuously, what I want is I just want to break into this trap routine and see how things are and what has caused this interrupt. Okay, so to keep a breakpoint in this Since I haven't enabled or compiled with the debug enable flag, I wouldn't be able to use this symbol names. So what I'm gonna do is, so these are all the symbols in the ELF, and this is a trap routine. So I just want to keep a breakpoint on this address. So remember that since this is an address, you need to prefix with the star. Okay. So let me run now. Oops. Oh, I did not load the code. I'm sorry. So load. Sorry. Four breakpoints. Okay, have a breakpoint in the trap routine. Let me continue now. Okay. So you see, whenever there's a change in the signal, the execution jumps into the trap routine. But here we can investigate few things. One is what has crossed the trap. Info register mcos. Okay, I'm also reading this mcos value into T0, but since this is a hardware register, we can directly read from this. But if you pay attention to this, and if you see the manual, let's see the manual. So mcos. See here. So the most significant bit will be set 1 if that is an interrupt, and if it will be 0 if it is an exception. And B means machine external interrupt. Okay, so that's good. So because this is an external interrupt, so that's right. Then let's go further, and what else we can see. Let's see if you see here, let's go to the PLIC. So this is the FE310 manual. And GPIO, is there any interrupt pending? There should be a, yeah, let's see. So RISC interrupt pending should be at this offset, and the base address is this. So at 0x10012001C, that should be an, let's examine that memory. So 0x1001 and 0201C. 201C. You see here? So this is, if you see the bit position, that would correspond to bit 21.0. This should be 21. And that means that 21 is GPIO 21. There is a interrupt pending on this when it came inside that trap routine. So that's right. And what else? This is on the GPIO end or at the interrupt source end. Let's see at the PLIC end interrupt pending bits. So this is the base address, and the first register has the interrupt pending bits for the first 31 interrupt sources. So if we inspect this memory location, 29th, because the interrupt source for GPIO 21 is 29, so 29th bit should be set at this location. Let's see that. So X and what was our address? 0C00. So there is one another, but this is the 29th bit, 0, yeah, 29th bit. So both at the GPIO source level and as well as at the PLIC level, those corresponding interrupt pending bits are set. So this function would clear the uh, interrupt pending bits on the GPIO, and then let's see what happens. Okay, I'll just step in. So right now it's here. I'll just run through this pending bits and it'll clear. Okay, so now it has come back to this function. What is that? TC. Okay, now let's inspect those two pending bits. This one and this one. If you see here, so the clearing the interrupt pending bits on the GPIO clears that, but if you see that the pending bits on the PLIC is no, what is this? This is the GPIO that is cleared, but this is the PLIC which is still set. This would be cleared only when this interrupt is claimed. So let's go further. And you see here load. So we're gonna read this value from the claim register. So what is the value read is info register T2. So yeah, so the value claimed is 29. So that means that the interrupt source is 29. So if you see here, this is what I said before, like though we have enabled rise or high, low, or fall interrupts, that all will be converted into one single source interrupt. So just the interrupt for the source 29, and the target inside that trap routine, we have claimed that. So the moment it's claimed, if you see the both the pending the pending bits on both the so this one, see, it's cleared on both, because on the PLIC level as well, it's cleared. Okay, so now coming back to this diagram you see here. So to claim, we should read from this memory address. That's what it's done in the, so this is the address, and that it's claimed, it's read from that. And to mark the completion, we write into that. I think it doesn't matter what you write. So all you have to do is just write the value into this. So the same value is gonna be, if I step further, so the next execution would be the store that would be executed, and now it will return back. Okay, I'm gonna do is, so all good, and I'm just gonna continue. So this interrupt keeps occurring whenever there is a rise on that line. Okay, so what I'm gonna do is now delete, and I'll just continue that. Okay, so now all done. So that's the end of the session. So go ahead and feel free to use the code, or uh, if you have any comments on this, or if you need any clarification, feel free to post your comments on the questions on the comment section. Okay, thank you, and see you in the next session.